Hello and welcome to another episode from Spiral Physics Education. So we're going to be looking at efficiency in this lesson, and we're going to be looking at defining it to start off with. We're going to be looking at some language that we can use to describe why energy transfers are never 100% efficient in reality. And we're going to carry on with those terms, looking at using dissipated to explain what happens to that wasted energy, and in particular where it goes, because exam boards really like to hear that not only does that energy get transferred via a thermal energy transfer, but it also goes to the surroundings, and we call that dissipated. And finally, we're going to look at a few worked examples using power as work divided by time. So what is it that you're going to need to know for this lesson? Well, you're going to need to know about examples of stores and transfers, principle of conservation of energy, and because most of it is going to be based on three different types of calculations and examples, you need to know a few equations. So kinetic energy, gravitational potential energy, work done, and also power. So what is efficiency? Well, to start off with, you can think of efficiency as a measure of how well a device can transfer a certain energy store into another useful energy store or transfer. And that's not really a definition, but that's how you can think of it to help you understand what efficiency is. In terms of the actual definition, it's a ratio. And if you get a question in an exam that says explain what efficiency is, you have to think of it mathematically. So you would have to say it's a ratio of useful energy output to total energy input, or you could use total power and useful power output. That really means that we've got this equation. So we've got efficiency is this ratio, so useful energy output divided by total energy input, or it could be in terms of work or in terms of power, but the numerator and denominator must be in the same energy quantity, both energy, both work, or both power. Sometimes you can expect to give your ratio as an answer in terms of percentage, and if you do that, then all you need to do is multiply it by 100. But the top equation, the answer would always be less than 1, and the bottom equation there, the answer would always be less than 100%. So exam boards often like to ask questions that go on the base of how to improve efficiency, and the only way to really get your head around this question is to think of the equation. If we've got the equation like this, then once you realize that the total energy input is fixed in a question, you can't change that total energy input, then the only way to affect the efficiency is by looking at how to change the numerator, i.e. how to make the numerator as big as possible. So how do you make the useful energy output as big as possible? Well, the only answer to this is to reduce the wasted energy. And you need to understand where that wasted energy goes. So that wasted energy is mostly in the form of a thermal transfer of energy to the surroundings. And the key words there are wasted, thermal transfer, and surroundings. And you can even use, if you're feeling particularly confident, the term dissipated. So thermal transfer of energy dissipated to the surroundings is the best way to describe what happens to that wasted energy. So if you can improve efficiency, you can improve efficiency by reducing that thermal transfer to the surroundings. So let's have a look at a slightly different approach to efficiency, but still using a kettle. So in this one we've got a kettle that has a power rating, and that 2000 watt kettle is going to deliver 39 kilojoules over a period of 30 seconds to the water. Now here we've got units that are a little bit strange, but we've also got two mixed quantities. We've got the power rating and energy, and we can't use this equation with one being energy and one being power. They've both either got to be both energy or both power. So I'm going to approach this in terms of power, because the kettle's power rating is 2000 watts. That's the total power input. I've got that already, but I need to know what the useful power is. So if I think about power, that's work done divided by time taken. So the work done is that 39 kilojoules, but I've got to do it in terms of joules. So that's 39,000 joules divided by 30 seconds. And that will tell me the useful power is 1,300 watts. So now I've got my useful power output, I've got my total power input. I can substitute that straight into my equation, and I get an efficiency of 0.65, or if you prefer, 65%. Okay, so we've got our final and hardest example to work on now. So this time it's going to be a car. And we're going to look at this car increasing its speed from 5 meters per second to 8 meters per second. And during that time, 60 kilojoules of chemical energy store is going to be transferred to the car. So looking at that kilojoules, we've got to be aware of that. And if we get an opportunity to use 60 kilojoules, we've got to make sure that we use 60,000 joules. So I'm going to use this version of the equation this time. So we're going to have work on the top and work on the bottom. But I need to identify what the useful work output and the total work input is. So the total work input is going to be that 60 kilojoules. That chemical energy store is going to get used up, and work is done when energy changes store or moves between stores. So that 60 kilojoules is going to be my total work input. So what's my useful work output? Well, that's going to be the change in the kinetic energy of the car. So it goes from 5 to 8 meters per second. That means its speed increases. That means the kinetic energy increases. And if energy increases or changes store or moves between stores via transfers, work is done. So I'm going to look at that useful work as a change in kinetic energy. And I'm going to use this equation for that change in kinetic energy. So if you're unsure about what that equation means, or it scares you a little bit, check out the video on kinetic energy, just to get you a little bit more confident about using that equation. But I'm assuming at this point that you're quite confident in using that, understand what those terms mean, and can do that calculation with little or no hand holding. So the V is going to be 8 meters per second, and the U is going to be that 5 meters per second, and it's a 1500 kilogram car. I'm going to plug that in and just check that though for me. It's going to be 29,250 joules of useful work done. So now I've identified my useful work done. The total work done is the 60,000 joules of chemical energy store, and that gives me an answer of 0.49, or if you prefer, 49%. So that's it for efficiency. Thank you for tuning in. Hope it helps improve your understanding of efficiency and helped you look at a few different examples of how to calculate efficiency and get as many marks in that exam as possible. Don't forget to subscribe to the channel, and see you next time on Spiral Physics Education. Goodbye.